Hello everyone, today we'll talk about the solution to the problem best sightseeing pair. There are a couple of problem-solving approaches, problem-solving, let's say, patterns that we can use to solve this problem. I'm going to share my favorite, because it's not always that you can use that particular technique, and this is the thing that I have implemented. However, there are also other approaches, so maybe let's start with something more general. One general approach that can lead us to a solution here is thinking about monotonicity, or thinking about elements dominating each other. This is a line of reasoning that can often lead to optimal solutions to problems. Often those solutions are based on monotonic stacks. And it's rooted in the idea of one element dominating another element. That is to say that if there are two elements and one is dominating the other, then we essentially can forget about the dominated element. The dominating element is better than the dominated element. And we can see that this is indeed the case in this problem. Because if we have two different values, let's say that we are going over j, iterating over j and finding the best I for every j. This is also what I am going to do in my solution. And this is a very standard approach. So let's say that we want to find the best I for every j. And if we have two different candidates for i's, and one is better than the other, which means that values of I0 plus I0 is better than values of I1 plus I1, let's say, then if we move to some further j, then those two values are still ordered in the same way. So if at some point one I is better than the other, then it will always be better than the other. And that is a classic monotonicity or domination, right? But you might have noticed here that, because typically in a monotonic situation, we would say that, well, the score, of course, if we increase j, then the score will decrease by 1 for every step, something. But this part that depends on I doesn't change at all. The value that the element at position I contributes to the final value is values of I plus I, and it completely doesn't depend on j. And this is this more specific technique, which I prefer, because it's not always applicable, when you can essentially take the thing that you are calculating and rearrange it, rewrite it in some way. And the proposed rewriting here is that, okay, values of I plus I doesn't change, so maybe instead of looking at just the values list, we can look at the list of value plus index, for index value in enumerate values. So we put this plus I element into the values. And now the final result here would be values of I plus values of j minus 2 times j. Because we have minus j here and we've also here added j, so we have to subtract it again. And so what is the best I for a given j? Well, it's just the maximum, the I that gives us maximum values of I up to j. And the score that we would get for a given j is just this maximum plus the value of j minus 2 times j. So we'll be maintaining our maximum, we'll be remembering our best, and at position j, we can try to improve our best by values of j minus 2 times j plus the maximum, and this is the maximum values of I. And of course we have to update the maximum. And at the end, we of course return best. So this is a very simple application of that idea of just rewriting the objective function so that it becomes easier, or that it stops depending on one of the two indices or something like that. And it's very useful because it's less obvious than the classic monotonic or domination-based approaches. But anything that will work here, of course, will work. It's up to your preference.